All right, thank you very much for the invitation. So today I'm going to be presenting joint work with Alex Gambord and Michael McGee. Okay, so I will start with by writing down an equation that will look familiar from earlier today, and that is the Markov equation. So typically we write the Markov equation as a sum of three squares that is equal to the product of those numbers, and then multiplied by either 1 or by a 3. Usually I'll write it here with a 3. So this is the Markov equation. And the problem of counting solutions to the Markov equation, where the maximal entry is less than or equal to r, that asymptotic counting problem was first investigated by Gurwood in 1976, and then further refined in Zagier's work. So I will state Zagier's result from 1982. Which says the following, that if I look at the number of solutions that lie in a ball of radius r, so using the notation from earlier today, let's say that this variety is x. If I take the positive integral solutions and I intersect with a ball of radius r with respect to the L infinity norm, this is something like a constant times log r squared, plus some big O error term. So the error term that Zagier got in his result was big O of log r times log r squared. OK, so this is Zagier's result. Like I said, this is not the first result on the problem. It's also not the current record result, so this error term has since been improved. The current record removes this squared in the big O error term. But it is Zagier's result that I'm stating because his result is sort of, his techniques are very relevant in what I will be talking about today. Today what I will be talking about is the n-variable generalization of this Markov equation, which I will refer to as the Markoff-Hurwitz equation, which is so named because it was first studied by Hurwitz. So let's see. Let's put this up here.
So Ronan translated Hurwitz's paper into English as part of his German exam.
Yes, that's right. So I have first-hand experience with this paper. So what is the n-variable generalization? Instead of looking at the sum of 3 squares and comparing that to the product of those 3 numbers, now I'm going to take the sum of n squares and compare this to, let's say, x1 times x2 up to xn. In terms of the coefficient to put in front of that product, we'll just leave that as a parameter a. So here a is an integer greater than or equal to 1. Here I'm looking at least 3 variables. This is the version of the equation that Hurwitz studied. But in a lot of what I talk about today, I can deal with a slightly more general equation. We can add an extra parameter k at the end. So here k is a positive integer that we can address. If k is negative, our results don't go through. That's not to say that the equation is not interesting, but the techniques fall apart. Okay. So let's see. So the
I think this is a subtle issue, and we can say some things and there's exceptional solutions. I think it's best to If there is time at the end, I think we can revisit it. But this is a settled point.
If k is negative, doesn't that just mean you can put it on the left-hand side and imagine them all being ones?
That's what Hurwitz does. That's not for the purpose of counting. That's introducing more variable there.
There are also exceptional solutions here. I think it's best to return to this point at the end.
Okay.
Yes, the plus k actually, it complicates things at the beginning of the argument, but sort of in the bulk of the argument, it eventually gets swept under the rug and addressed early on. But OK, I'll put that general version of the equation there. The problem of counting solutions to this more general equation, at least in the case where k equals 0, this was famously addressed by Professor Baruch. It's a little strange referencing him. I just met him a few moments ago, even though I've been reading his papers for a while. In a series of papers in the 1990s, Baruch approaches this problem of looking at Zagier's count and trying to see if there is a similar looking formula for this n variable case. We look at Zagier's formula, and I think the natural first impression is that that log r squared term that shows up in Zagier's formula, particularly that exponent of 2, it seems like maybe that's one less than the number of variables. So if there were a similar looking formula for the n variable case, we might expect it at first glance to look something like a constant times log r to the n minus 1. That was at least my first impression, but that's not the case, and that is what Baruch showed. So I'll state the results. This was in a 1998 paper, which says in some form that, let's say for k equal to 0, if I'll say this is the variety x, n, a, k. So if the set of positive integral solutions is non-empty, and k is equal to 0, then we have the following estimate for the number of solutions. Turns out that the number of tuples here we can write as log r to the beta plus little o of 1. So here that error term is in the exponent of the log r. This number beta here is sort of very interesting to talk about, though, because like I said earlier, that beta is not n minus 1. So in this work, it was shown that so beta is a function of only n. It has no dependence on that parameter a. Zagier's work, of course, gives that beta of 3 is equal to 2. But the beta of 4 is not 3. It is somewhere between 2.43 and 2.48. And beta of 5, it's not quite 4. It's actually between about 2.73 and 2.80. In general, beta of n is something like log of n minus 1 divided by log of 2. And in this work, there are some bounds about exactly how close beta of n can be to this log of n minus 1 over log of 2. So this is it's a surprising and kind of mysterious result. It's not quite what we would expect.
Baruch's work, I guess I'm going to skip that one. Is beta given in other terms?
OK. So
in other words, there's a solution to some equation or some fixed point or something? Or
the beta.
value of some.
I think you should ask author, because we are not contributing anything to. I mean, we are giving interpretation, but author is a person to answer this question.
I was the speaker.
Well, please correct me if I'm wrong, but my
Yeah, how did you identify the number as what? Beta is what? Is there some limiting process, or is it?
It's a critical value, so of a function that diverges on one side and converges on the other side. sort of, you do a self-similarity argument.
That's like an Hausdorff dimension or something?
It's kind of like counting that. So you go out in a tree and you get some sort of coefficient to the front, except that it's a function. And then if that function is larger than 1, then you must
Yeah, so it's like a
include
critical
the-
exponent, so it's
Right.
defined through real analysis. Okay.
Yes.
Place where something changes behavior. Yeah, okay.
Well, yes, it's an interesting question about this beta, and is there another way to interpret it besides as the exponent that shows up here? And this was a question that was actually asked by Silverman. Silverman was asking about this number beta. Is this number beta in general irrational? Is it transcendental? Is there a nice closed form expression for beta? So the beta remains mysterious. Silverman was also, when discussing this problem, asked, is it possible that there is a true asymptotic formula in the sense of Zagier's result for this more general n variable case? So in our work, what we are able to do is answer that second question. We are able to recover a asymptotic formula where the main term is a constant times log r to the beta, which I will write down in a moment. But that second, or I guess that first problem where we ask more about the nature of the beta, that remains somewhat open. So our work does offer some new interpretation of the beta, but it doesn't really necessarily give any sort of closed form expression. The beta still remains mysterious in some way. OK. So let's see. So to properly state the result, this plus k when k is non-zero, there is some technicality that needs to be addressed. It turns out that if k is greater than 0, there may be these exceptional solutions. Which I will refer to as the set script E. And the reason that these solutions may be exceptional is they exhibit a different quality of growth than what we expect from these formulas. It's not the type of growth we're trying to count. In particular, the growth of the exceptional solutions is at least linear in R. Somewhat conveniently, these exceptional solutions are possible to characterize. So it's not just that exceptional solutions may exist. We know exactly when they should exist and exactly what values of k and a seem to produce these. And they're sort of easy enough to remove from the counting formula. And then we can see exactly the main term that we want to be seeing. So the result, this is the joint work with Gambord and McGee from 2016. Says that if the number of positive integral solutions without the exceptional solutions, if they exist, if this set is infinite, this is a stronger condition than what was needed over here. Again, that comes from that parameter k, which sort of throws off the early part of the argument. But if this set is infinite, then the formula that we obtain is that the number of positive integral solutions with maximal coordinate less than or equal to r this is a constant times log r to the beta plus a little o of log r to the beta. So of course, a much weaker error term than what Zagier obtained.
So you don't get a parasitic?
Uh,
I mean, log r to the beta minus epsilon in the error term.
correct. We don't get that. We don't get that.
In this paper, we don't have.
Yes. Yes, correct. OK.
I mean, in the work of Rubin and McShane, they just have this domain and it's just counting lattice points.
Yeah, that's a volume of the, but they use interpretation
lattice point counting
as a modular space.
Ah.
That's what Belly does also.
Yeah. Now then it's clear you go down to that immediately and then.
Also in their work, the value of C has a very very clear meaning. It's a
Right.
volume of the.
Yeah.
We don't have interpretation for C.
Same as Apollonian. There's some interpretation.
But in the Apollonian, you don't have a power savings limit?
Yeah, we,
Oh, you do?
Well, it's the same. It's the same result as Lally gets. So when Lally gets, it's the same result. But the value of C is Agia's work via the work of Reading and McShane and Belly as a meaning as a volume of the known one ball in the Tachner space.
but Lally actually gets prime numbers. Okay.
No. I'm talking about C in front of Luhar square. That's a volume.
Sure. But the first thing you said was about the error change. You get the same error as Lally.
Basically, yes.
So you can get a
We can.
e to
But
the
we,
minus root log there.
we can. But we didn't precisely display.
Yes.
Does infinite not follow from non-empty?
It does not if k is not 0. And the reason why this infinite descent, so you know what, I will get to that in a minute because that's relevant to the next step over here. So let me say something about this infinite descent, which came up a little bit earlier, and it's crucial to getting any of these sorts of counting arguments to work for this particular equation. So it turns out that outside, well, okay. I should say something about the moves in this setting. So earlier today we talked about the Vieta involutions for the Markov equations. For the Markov equation, this generalizes very nicely for the n variable case. So maybe from here on out, just to make the notation a little bit easier, I will assume that a is equal to 1 and that k is equal to 0. And then I can define the following moves. You can call these the Markov-Hurwitz moves if you would like. So if x is a solution, then if I put x into this map that I'll call lambda I, what this does is it removes the ith coordinate and it replaces it with the new coordinate that you would get by viewing the Markov-Hurwitz equation as a quadratic in xi. So the way I will write this is, let's say we have x1, that stays the same. I remove the ith coordinate, so that notation means I omit that coordinate. I slide all of the other coordinates down, and my new last coordinate is going to be the other root of that equation. This is the product of I not equal to j minus the original ith entry. Okay. And these moves make sense when I is between 1 and n. 1 and n. OK, so these moves are somewhat well-behaved outside of a compact set. So, and that's where this infinite condition comes from. So this part of the argument, this was known in some sense dating back to Hurwitz. Outside of some compact set, which I will call K, we have the following properties. If x is a tuple, a Markov-Hurwitz tuple, and let's just assume that x is ordered for a second. So the coordinates of x are non-decreasing. This is an ordered x. Well, then it turns out that if I apply lambda I to x, if I is between 1 and n minus 1, this will raise the largest coordinate. And that's part of the reason why I wrote this new coordinate in the last entry. Again, if I is not equal to n, and as long as I'm outside a compact set k, and as long as x is ordered, lambda I is raising the largest coordinate. So lambda I of x, the nth coordinate of this is larger than the nth coordinate of x. This is for I between 1 and n minus 1. The nth map over here goes in the other direction. So the nth lambda, that's going to decrease the largest entry. So that corresponds to going backwards on that tree that we saw earlier in the Markov case. So lambda n of x, the nth coordinate of that is less than xn. Okay. Okay. No, this is. Yes.
Exactly.
Yes. Yes. OK. So these two properties, together with the fact that we can guarantee that the largest entry of x is unique, again, outside of that compact k, this gives us that infinite descent argument. The presence of a non-zero k, that could mean theoretically that this compact k are the only solutions. So having infinitely many is important to make sure that it can get out of this compact k. That's where that comes in.
Sorry, say that again. You're assuming the largest out values are, you have some version of unicity?
Sorry, what was the last one?
Some version of unicity, that the largest entry is,
No,
what did you say?
OK, the largest entry in that tuple is unique with respect to the other coordinates in that tuple.
I mean, strictly large.
Strictly larger,
Okay.
yes.
You already-
but it's not unique.
Yeah.
Yes, sorry. Good. OK, so this gives us the infinite descent argument. And with this argument in mind, we can translate the count on the original equation to account of the orbit of these maps lambda I on an ordered tuple, provided that there's no issue changing the problem from unordered tuples to ordered tuples. And surprisingly, this is not a trivial issue when n is greater than 3. It's not a hugely pressing issue. It's solvable with a little bit of work. But when n is greater than 3, you may or may not have repeated entries that are not the largest entry. And that means the multiplicity of the ordering map is not necessarily constant on the variety. So changing between the non-ordered problem that we start with and this ordered problem, again, not completely trivial. There's something to check there.
You could presumably localize this into a piece, a sector of the tree. Then all these problems disappear.
Probably.
Uh,
This problem will disappear.
Yeah, you can localize where all of them are roughly the same. You know, this is really.
That's probably roughly. That's probably roughly what. That is in some
Once
sense.
you get one entry to be strictly larger than the others,
Yes.
why don't you just do this, once you're outside the compact set, just do this on every entry, and then they're all strictly larger than.
Because you could, if you iterate lambda n minus 1, say, repeatedly, you're never changing these first n minus 2 coordinates.
So once you have the largest one, once you're
Yes.
outside the compact set,
Yes.
and you get the largest one to be strictly larger,
Yes.
then you hit it with lambda n minus 1, lambda n minus 2, all the way down to lambda 1.
Right, but I can be outside. So say I'm outside the compact set and say I have repeated entries somewhere.
Yes.
That means I can increase my largest entry some more without changing those repeated entries.
No, but if you're hitting every entry, if you're
Anyway,
following-
I think you can localize the problem.
OK, yeah, I mean, yeah.
Probably what you suggested is cleaner than what we did.
That's how you normally get around this when accounting in space where there's an issue of permutations.
Yeah.
You just localize.
But this is sort of a
Yeah.
prequel to the real argument.
OK. 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 OK, so we've essentially translated the problem from counting the original solutions to counting the orbit of this semigroup generated by the lambda I. So I'm going to write capital lambda as the semigroup generated by lambda I, where I is between 1 and n minus 1. OK, and the next step of the argument is to, we in some sense want to linearize this problem. These maps lambda I, they're nonlinear, and that makes life more complicated. But there is a standard way to linearize this problem in the following sense. If the xn is very large, the left-hand side of this equation looks something just like xn squared. So if I take the log of both sides of the equation, I get that approximately log of xn is about the sum of the n coordinates. 2 log xn, although if I subtract a log of xn from both sides, I get this equation. So I'm led to study the following hyperplane in Rn. Whoa. where I look at positive real n tuples that satisfy the equation that the sum of the first n minus 1 coordinates is equal to the nth coordinate. Okay. And here I want the yi to be non-decreasing. And yeah. The nonlinear maps that I talked about before nicely correspond to this linear problem in the following way. I get the map gamma I, where I replace the ith coordinate. Instead of that product minus xi, it just becomes the sum of the yi. So I sum over all yj not equal to I. OK. So our attempt to change this nonlinear problem to a linear problem is crucially dependent on the quality of this estimate. And this is where our work starts to diverge with the previously mentioned work. So this observation was known to Zagier, and he uses this in some sense. But Zagier's stronger error term essentially comes about because Zagier is able to use a function which makes this estimate better than what log gives us. So the function that Zagier uses is something like arc-cosh, and that
the function, by the way, which converts Markov surface into K is that arc-cosh function is.
I see.
Okay.
That's what.
With the change of K.
Yeah. Sorry.
So Zagier's function is a little bit better fitting, but that's very particular to the 3-variable case. So we are stuck with this log, and there's something to be said about the quality of this estimate. And let's see. So what could go wrong here? The estimate will be weaker if n is not much larger than xn minus 1. So when exactly could that happen? Well, if the first n minus 2 entries are very small, that product on the right-hand side, for that right-hand side to match the xn squared on the left-hand side, that means that the xn minus 1 has to do a lot of heavy lifting. And the xn minus 1 is sort of forced to be large if the product of the first n minus 2 entries is very small. So in some sense, this estimate is only good. One way to word this is that the product of those first n minus 2 entries must be small. So we can write this quantity as alpha of x. This is the product of xi, I from 1 to n minus 2. I want this alpha of x to be very large. Here's the issue. These maps lambda I, OK, they increase the largest coordinate. But there's one map here that actually does not increase alpha of x. Lambda n minus 1 only changes the last 2 coordinates, which means I can apply lambda n minus 1 repeatedly to x, and I'm not changing this product at all, which means I could theoretically have a word which is very long in the generators of lambda, which does not change the quality of this estimate. And that makes the analysis part of the argument where I fit the nonlinear problem to the linear problem very difficult. I want this alpha of x to grow in the word length of the generating set. So there's a problem here. There's an issue that needs to be addressed to make the quality of this fit strong enough to get the estimate that we want. The solution to this problem is to replace the generating set, lambda 1 through lambda n minus 1, with a new generating set. And this is our crucial idea that really helped us make some progress on this problem. So we are going to replace that generating set with what I will call, let's see. So I'll define it in terms of the maps gamma, but this translates back to the moves lambda in the natural way. I'll say T gamma is the countably infinite set of maps, gamma n minus 1 to the a, composed with gamma of I. So here I is between n minus 2, and a is a number greater than or equal to 0. And then rather than work with the maps generated, rather than work with the semigroup generated by all of the maps in the way we did before, I'm going to look at the semigroup of maps gamma prime generated by T gamma. So we call this the acceleration in the problem, and that terminology was used in a 2006 paper by Zorich. That's where we got that terminology from, this acceleration. Why is it an acceleration? We're viewing all of the gamma n-1 moves at once.
It's a standard thing to do if you have, in the thermodynamics, when you have parabolic elements, then you're not growing exponentially. There's no hyperbolicity in that direction. So what you do is you make an infinite word, infinite language, alphabet.
Yes.
Which is exactly what this is.
Yes, exactly.
This goes much further back than just storage.
Sure, yeah. I just mean the terminology of acceleration. Oh, OK. Well, my blunder.
We learned this from Zorich's paper, and subsequently, of course, Zorich was not the first one.
OK.
Probably, I don't know, I'm silent.
This acceleration idea, it solves this problem with this fitting part of the argument. It actually also solves a related problem later on in the argument once you translate it more directly to a dynamics problem, which is related to that question. OK, so it's switching to this infinite alphabet is not completely trivial. For starters, I lose some of the words that were in the original semigroup. So any word that started with a lambda n-1 map or a gamma n-1 map, that's no longer in the semigroup. So we have to account for those separately. But this is doable. And it turns out that this fixes all of the analysis parts of the problem that show up in this fitting argument. So with this idea in mind, we're led to study the action of gamma prime on the hyperplane H. OK. Fantastic. Sorry, what time are we ending? 10 minutes left. OK. So what can I say here? Let's. OK. OK, so to count the, OK, so we have this problem where what we are left with is we want to count we have the sum of indicator functions, where I'm going to sum over all of the words in this semigroup gamma prime. OK, and I'm going to put these indicator functions. I'm going to check if gamma acting on some fixed y in the hyperplane is that nth coordinate less than or equal to some number, let's say a, which was related to our original r. So we get this sort of sum of indicator functions. And we rewrite this sum in such a way that it satisfies a recursive identity called the renewal equation. The reason why we do this is there is a technique due to Lally, which turns this renewal equation on the sum of the generators of this semigroup. It turns that renewal equation into an estimate for the count itself. And the way this works is by taking the Laplace transformation of the renewal equation that you get, and then inverting that Laplace transformation by looking at something called the spectrum of the transfer operator, using, say, the Ruel-Perron-Frobenius theorem. This part of the argument is not completely trivial because the Ruel-Perron-Frobenius theorem that we would need, the conditions to use that theorem are not completely satisfied in our setting. So we need to prove a slightly different version of that theorem. The main ingredient to use...
Is this a theorem which will isolate this Perron-Frobenius spectrum in its absolute value from the rest?
Yes. So this is we want to pick out the leading eigenvalue.
This is like a generalization. The generalization of Perron's result due to Wheeland, I think.
I understand, but that usually is a tricky point.
It is tricky.
Yes. And in particular, the trickiest part here is we need, for essentially to get that result on the spectrum of this operator, we need it to be the case that the generators of gamma prime, sorry, I wrote this wrong. These are not just the generators. I want the entire semigroup. We need the semigroup to be uniformly contracting in the generators of gamma prime, specifically uniformly contracting this hyperplane, or actually the projectivized hyperplane is what we wind up looking at. The reason I'm bringing this up is that issue, that uniform contracting issue, goes back to this part of the problem once again. Because if we did not accelerate, not only would the quality of this estimate have been weaker, if we did not accelerate, that uniform contraction does not go through and we do not get Rel Perron Frobenius.
If you have, so you have this operator, this Rel operator.
Yes.
The spectrum is in a circle, I assume.
Yes. Yes.
You got this Perron Frobenius guy that's got the biggest absolute value.
Yes.
You're proving that all the other eigenvalues are. What do you know about the spectrum? It's discrete.
We do not get discrete, but we get that the leading eigenvalue is isolated. It's bounded away from the rest of the spectrum.
You should definitely get a. Then of course you will get a Riemann term.
Okay.
That always translates to a Riemann term if you have a gap.
Okay. Well, we can't say that.
Yeah.
Okay.
Can you draw the spectrum?
Well, conditions. Well, not the spectrum, but maybe you can draw the picture for n equals 4, the triangle.
Sure.
The spectrum is just that picture. I think is very instructive. For n equals 4, the three maps and y will get a fractional. You know what I mean?
Yes, yes, yes. OK, so in the n equals 4 case, what sort of picture do we have of the hyperplane itself and the action of the generators on that hyperplane? So I'm going to draw this in 2 dimensions. I'll draw the projectivized hyperplane. So we're losing a dimension by projecting, and we're losing a dimension because we're on this hyperplane. So we get this 2D picture. The image of this region looks something like this triangle. And then we want to see how the generators, well, OK, let's just say how gamma 1, gamma 2, and gamma 3 shrink down this triangle. So what you get is something like gamma 1 maps this entire triangle into a triangle that looks like this. Gamma 2 maps this big triangle into a triangle that looks like this. And gamma 3 maps this entire triangle into this bottom part over here, which notably is much bigger than the other 2 triangles. We're left with this hole up here. So when we keep iterating this, we pick up another hole, or not just one hole, we pick up many holes every time. So as we continue to iterate this, we end up with this fractal attractor region with these many holes throughout. OK. One other comment I should make with respect to using Lally's technique, and that's also related to that spectrum question, is the operator that you get is parameterized by S. It turns out that the unique real number so that that operator has leading eigenvalue equal to 1 is exactly the beta that showed up in the main result.
Is that equal to the Hausdorff dimension of that fractal? Do you know that?
That is the natural first assumption, but it does not appear to be the case. And intuitively, the reason seems to be that these triangles are kind of skinny. They're not kind of shrinking in a...
The dimension here has to be less than 2, right?
Yes, the dimension is less than 2, but it does seem...
Somehow correlated.
Right. The Hausdorff dimension is certainly not the same as beta. That we know for sure. It does...
It's conceivable that there is a simple relation between the Hausdorff dimension and
Actually, I'm beginning to understand something. You never showed your beta was equal to his beta. It's just that the 2 theorems are correct, so that's why they're equal. Is that true?
Yes, that is true, and that is a subtle point that's in the paper. Yes.
You can't directly show.
Yes. Correct.
But from your interpretation of his, you don't see what.
Correct.
But
Correct.
it is most likely true that there is a relation between has the dimension and beta, and it is a simple one.
Can you just draw the spectrum again for me one more time? So you have a circle. When you apply you fix it up so that you're not going to apply this Arrhenius eigenvalue. So the spectrum looks like what?
So you have a leading eigenvalue over here that I'll call lambda s.
Wait, is that the spectrum of the resolvent or of
The spectrum of the transfer operator, which I didn't write down. The transfer operator itself. So I have a leading eigenvalue, which is positive, as long as s is positive. Sorry, I mean s is real. S is real. I'm working in the case where s is real. And then everything else is bounded away. So there exists an epsilon so that the rest of the spectrum is.
Whole radius less than lambda epsilon, strictly less.
Yes. Yeah.
Yes.
All right. That's a very small statement. Okay.
Yeah.
So we can get an error.
Yeah, you can definitely.
Correct. Well. Yes.
What is the relationship between the parameter capital A and the analysis of parameters?
This A here. This A just refers to how many times am I applying the map gamma n minus 1.
You don't choose it. I
No.
mean,
The A, this includes all values of A. So this is an infinite collection of maps.
This is only when s is real. To get that.
Okay. So I'm sorry, am I ending at 5:05 or 5:10? Or 5?
505. You got 2 minutes.
2 minutes? Okay, so I won't write this down, but just to sort of speak out loud for 2 minutes. In the talk earlier today, in Alex's talk earlier today, there was some discussion about taking the tree that you get in this problem and reducing it mod p, say mod p for a prime, and talking about whether this is connected or not. If you want to explore a similar problem and also say something about whether the solutions to the n variable case are almost always composite and get the analog of that theorem in the n variable case, one of the key ingredients that you need is something about the number of solutions mod p being asymptotically equidistributed in some sense that you can make precise. What I showed, which is not part of this joint paper that I presented, but was part of my thesis, was that under a certain connectivity condition, when you reduce these trees mod p, you can essentially use this argument with a few changes where you change, say, this indicator function to a vector value indicator function that keeps track of the congruence class of the original tuple. You can redo the spectral part of the argument. It's a little bit more complicated, but nothing too terrible, to get that asymptotic equidistribution that you would need for the generalization in the n variable case. And that's conditional on the trees being connected when you reduce the mod p.
So it's unconditional. For Markov, it is unconditional. Basically.
Yes.
After
Yes.
paper 2 is complete.
Yes. Sorry, in the n variable case, where n is greater than 3. Sorry, you had a question?
Not just connected, but expanded.
If you had expansion, you would be able to get a explicit error term in that argument, but you only need connectivity to get the type of formula that you want. You get a very weak error term. You get the error term basically what we have. Yeah.
Okay, let's thank the speaker.